We've already seen that there are a number of situations in which polar coordinates are more natural than rectangular coordinates. Polar coordinates, if you recall, are measured relative to what we call a pole and a polar axis, where a point in the plane is specified by the angle of a line directed from the pole to that point as measured in the direction counterclockwise from the polar axis and by the distance of that point from the pole. In polar coordinates, the simplest region to describe is a region of this type, where we have R1 less than or equal to R less than or equal to R2, and theta 1 less than or equal to theta less than or equal to theta 2. That can be depicted if we have the pole here and the polar axis here. We have an angle theta 1 and an angle theta 2, and we have some distance R1, so we're going to have a circle of radius R1, and I'll draw just part of such a circle. So this is part of the circle R equals R1, and another circle, and this is part of the circle. We'll say R equals R2. So we have the circle R equals R1, the circle R equals R2, and the region that's defined by this set of inequalities is clearly just this region right here. In order to represent small area increments, and we need to use small area increments to do integration in the plane, we consider a small increment delta theta and delta r. What we mean by that is, if this is our pole, we're talking about a very tiny angle theta, and I'm going to draw it a little bigger so we can label things. But here's a small angle delta theta and a delta r, some small interval delta r. Now delta r might be like so. So we have a delta r between, well, okay, we have an interval defined by the increment delta theta and the increment delta r at a sample point somewhere in space, or somewhere in the plane. And the sample point is going to have coordinates r, debating about whether to put a subscript on it. Let's just say for now r star theta star. So we have the r and theta coordinates of what's going to become a sample point. The question we want to answer is, well, what's the area of this delta theta delta r region? In rectangular coordinates, of course, we'd have a delta x and a delta y forming a rectangle. This isn't a rectangle. These are arcs of the circle. These are straight lines. But we can see that if delta theta is very small, this isn't too much different than a rectangle. The reason being that a line of constant r is going to be perpendicular to a radial line, and the theta coordinates run along radial lines perpendicular to the arc coordinates. So if r is a constant and theta is a constant, then this radial line will meet the arc of the circle of radius r at a right angle. Now we still have a little curvature here, and also as we move away from the pole, the interval gets wider and wider. So the size of this interval depends on two things. Given delta theta, it depends on the delta r, how long it is this way, and it also depends on the r coordinate. The bigger the r coordinate is, the wider this region is going to be. If we enlarge the region somewhat so that we can label it, we have our sample point, we have our two sides here corresponding to our two angles, and we have these sides here where I'm going to exaggerate the curvature a little bit. Each of these sides is an arc of a circle of some radius, and that radius is close to r star. Assuming that delta r is small, then there isn't much difference between r star and the radius at the closest and the furthest point from the pole. At our sample point, r star theta star, the arc has length r star delta theta. Definition of angle, definition of radian measure, tells us that the arc distance along a circle of radius r corresponding to angle delta theta is r delta theta, so that the arc distance is r star delta theta for the arc that passes through our sample point. It follows that the arc distance on the ends is also close to this. So if delta r is small, arc distance on the ends is approximately r star delta theta. So we can see our area increment as having two sides of radius of dimension delta r and two arcs of approximately equal to r star delta theta. Let's move over a little bit so we can see this. These arcs, if delta theta is small, this very tiny angle, these arcs are almost straight. So the arcs here and on this end are nearly straight, and circles centered at the pole meet radial lines at right angles. Without writing the qualification at the pole, we just understand that these circles meet radial lines at 90 degrees, so that these angles are very close to 90 degrees. So this angle here, and these angles up here that I'm not going to mess things up by drawing lines to. Our conclusion is that the area increment is, or let's say has, area. Okay, well, the area increment is practically a rectangle, dimensions delta r by r star delta theta. Which means has a length, if you wish, of delta r, a width of r star delta theta. So that when we partition a given region of space by small delta thetas and small delta r's, when we partition space regions by partitioning a theta interval and an r interval, we'll get sample points ri star theta j star within regions whose areas are going to be given by this expression. The area increment for polar coordinates is going to be r delta theta delta r. R delta theta giving us this side, delta r giving us this side of something that's very close to a small rectangle.